Good afternoon, everyone. Welcome to the security seminar here at Purdue University. Today, it's my great pleasure to introduce today's speaker, Jarecki. Professor Jarecki is assistant professor in computer science in University of California at Irvine. He received a PhD in computer science from MIT in 2001, and his research interests include cryptography and fault-tolerant distributed protocols. Today, Stash will talk about secret handshakes.
Thank you very much. Can you hear me?
Yeah.
Okay. Good afternoon. So this is the plan for the talk. I will explain what secret handshakes are. I will go over results from last year, which is a joint work with Claude Castelluccia and Jean Tsudik, where we construct secret handshakes and affiliation hiding encryption from computational Diffie-Hellman. And in the second part, about talk a new work with a student, Xiaomin Liu, on unlinkable secret handshakes. Okay, and mention some possible extensions, open problems. Okay, so we start from the picture of regular public key authentication. So in a public key infrastructure, you have a verifier and a prover who wants to prove that she's certified by some certificate agent, in this case, let's say CIA. Okay, so how does it work in a public key infrastructure? That means if she's certified by CIA, that means that she has a certificate, hers, which is Alice's certificate, that is signed by, which is a signed statement signed by CIA's public key on a pairing between Alice and some other identifiers and her public key. Okay, so first of all, she delivers that, and then she proves possession of a secret key that corresponds to this public key. Okay, so that's just how regular public key authentication is done, and what we notice, okay, so you might like it, we might not like it, is that this protocol has no affiliation privacy. Okay, so her affiliation, which is CIA, so apparently, she holds the certificate, she's a member of CIA group, is revealed in this protocol. Of course, it's revealed because it should be, right? Like Bob wants to certify, wants to check precisely that. Is she certified by CIA? So, so in some sense, it's like, well, it's revealed because it should be. But let's pose the following problem. So, can Alice control to whom she's going to reveal this affiliation? Or in other words, can Alice authenticate herself and reveal this affiliation only if the verifier, which is the Bob, passes some criteria as well? So, in other words, if Bob in place, for example, to simplify it, if Bob is also a CIA member, okay, if Bob also has a public key B and a signed statement by the CIA on a pairing Bob, etc., and his key, okay. But that sounds, so at first, it doesn't sound like a trivial problem because it sounds like a chicken and egg type of problem. So, who is going to go first? If Alice will reveal her certificate only if Bob possesses his, then so it's the Bob who should send his certificate first, and in which case his affiliation is not protected. Okay. So how do we do that? So let's. So here is the statement of the problem. We have, and in general, we have an asymmetric situation. Okay. So Alice is certified by some agency A, while Bob is certified by agency B. What that means? That means that Alice, in general, has some ticket issued by this certification. In the picture before, this ticket was a pair of a secret key and a signed statement on the pairing between Alice and the public key. But in general, it can be anything. okay, that cryptographically works. Let's call that a ticket. And moreover, Alice has a policy which states she's willing to talk to people who are certified by CAB, in particular, Bob. And symmetrically, Bob has a policy which says that he doesn't mind talking to people certified by CAA. Okay? So far, this is a regular authentication by, bidirectional authentication picture, except we want certain privacy properties of it. Okay? And the privacy properties are of two kinds. And then symmetrically for Bob, the same type. Okay? But for each of them, there's really two. So from Alice's point of view, Alice wants, first of all, to reveal the fact that she has a ticket issued by CAA. In other words, she's affiliated with CAA. She wants to reveal that only to people who are themselves affiliated with the agency that her policy states. Okay? So only if Bob passes the test, if he has a proper ticket, he should learn that she's affiliated with CAA to begin with. Moreover, there is one more property, okay? So that would protect the fact that she is affiliated with CAA. But another part of her, of what she might want to protect, is that she's the kind of person who's willing to talk to people certified by CAB, okay? That's also something you might not want to reveal. Trivially, in the symmetric case, where basically both of these guys are CIA guys, in this case, both CAA and CAB will just be CIA, right? So the fact that I want to talk to CIA people basically means I am a CIA guy myself, right? So it's really both of these things that should be protected. Okay, which is the second property. And of course, Bob wants the same type of protection, okay, against malicious Alice. Okay, so now that you stated like this, in particular, this is it's a two-party computation problem. Alice has some inputs, her ticket and her policy, and her ticket, affiliation, and policy. Bob has inputs, and if Bob has some inputs, and the output of this two-party computation problem should be basically just yes or no, only if they match on the diagonals, right? So if my policy matches with your ticket and my ticket matches with your policy. If the protocol output just says yes and no, it basically protects all the secrecy of the inputs, right? So we know by the general results in secure party computation, two-party computation, that there exists a protocol that solves this, okay? But these general results that tell you that the protocol exists and it's efficient too, the efficiency here is measured in polynomial time, and in particular, these basically they do not yield practical protocols. So the protocol that will result from general techniques would be linear in the size of the circuit description of this problem. Okay, so if you think about circuit description of signature verification, you have like thousands of gates already. Okay, and so this kind of compilation, generic compilation, is going to create protocols which might have, on the order of thousands or tens of thousands cryptographic operations. Okay, so we want